Here's an example of an improper integral. Just for a second, let me divert us away from the complicated part of it and just focus for a second on the fact that as antiderivatives go, this one's not bad. If this was just the integral of dx over 1 plus x squared, a quick substitution would turn this antiderivative into negative 1 over 1 plus x plus c. Okay. If you don't believe me, pause this, go off to the side, set u equal 1 plus x. Then you'll have an antiderivative of u to the minus 2, the power rule kicks in, etc., etc. Okay, so in this problem, the antiderivative action for this integral is not the big deal. The big deal is the fact that we have limits of integration here, which means by the fundamental theorem of calculus, you would like to be able to plug in these limits of integration and evaluate the antiderivative at those endpoints. But here's the problem. Let me draw a number line here. This integral is taking place from negative 2 to infinity. Essentially, we're finding the area under the function 1 over 1 plus x quantity squared from x equals negative 2 all the way out to x equals infinity. There are some uh-oh points in between these endpoints. For example, when x is negative 1, we have bad news. The fundamental theorem of calculus only works if your function stays intact over its entire range of integration. If we have an uh-oh point somewhere in the middle of our limits of integration, or in fact at one of the limits themselves, then we have to take a lot more care to do the problem. Infinity is an uh-oh point. Whenever it shows up as a limit of integration, infinity is an uh-oh point. And what we have to do here then is break apart this range of integration, negative 2 to infinity, so that we isolate the uh-oh points as endpoints of integration, and then we can do the integral within each piece. Okay? So in this particular instance, we would have to take one interval from negative 2 to negative 1 and stop the integration for a second, and then pick up on the other side of negative 1. We have to break the range of integration up at these uh-oh points. And so the next segment would look like this. Here's the fun part. Not only do we have to break up negative 2 to infinity to isolate uh-oh points as ends of integration, we are also only allowed to have one uh-oh point per interval. So this interval has two endpoints, negative 2 and negative 1. Negative 2 is fine. Negative 2 is not an uh-oh point for that function. Negative 1 is, okay? And that's fine. So this integral is safe. This interval is safe. This one, though, the negative 1 and the infinity are both uh-oh points, which means that we have to break this up one more time yet. So that we can isolate this uh-oh point in an interval by itself, and this uh-oh point in an interval by itself. Now, what point do we use between negative 1 and infinity to break this apart? Who cares? It doesn't matter as long as it's not itself an uh-oh point. So, what the heck? How about 5? Okay, 5 is a perfectly good breakup point there. And so what that means is to do this integration from negative 2 to infinity, we really have to break it up into three subintegrals over 3 subintervals by which we're isolating the uh-oh points so that we have no more than one uh-oh point as a limit of integration in any of these 3, and then the function itself is perfectly valid throughout the interval set up by these endpoints. There are no more uh-oh points hiding in these intervals. So this original integral got busted up into 3 individual pieces, and I'm not even rewriting the function that we're integrating because that's actually not relevant at this point now that we've discovered the uh-oh points. So that's step one. Find the uh-oh points and then break up the big integral into the sub-integrals that isolate the uh-oh points as endpoints of integration. The way we cheat the fundamental theorem of calculus here is to go look at these uh-oh points. Here's one, right? And here's the other. I've circled the uh-oh points. We got to get them out of there. The fundamental theorem of calculus doesn't work if there's a discontinuity of our function in between the endpoints, and it doesn't work when one of our two endpoints happens to be a bad point of the function, say not in the domain. So we cheat. We say, okay, fine, I can't use -1 as an endpoint of integration here. Then I'm going to pick a value a, and I'm going to get a different colored marker here, although you might not be able to tell it's a different color. I'm going to go up to my number line here. Let's just say that I'm going to put a right there. Right, a is pretty close to -1. And then what would we really like to see happen? Well, we would like to see what happens as a approaches -1 for the value of this integral. And now we've cheated the fundamental theorem of calculus. As long as a isn't -1, the fundamental theorem of calculus can be used on this structure. So we get the job done, and we say, okay, fine, fundamental theorem, I won't use -1. I'll go from -2 up to something which is really, really close to -1, but it's not -1, and I'm going to solve that integral. The antiderivative for the result will have a's floating around in it, and then I will ask the question, well, what happens if a approaches -1 in the limit? In this one, again, we have the uh-oh point. Try to put the function back in here. Fundamental theorem of calculus says, wait, you can't do this integral with a -1 there. And so we say, okay, fine, we'll get it out of there. We'll, instead of using -1, we'll find another point that's really close to -1. We'll call it b. B's not -1, but who cares? We'll still do it. So fine, we'll get that antiderivative, we'll evaluate it. But then, fundamental theorem of calculus, all I'm going to do is then turn around and ask, well, what happens to that result as b approaches -1? I'm smarter than you, fundamental theorem. And then in this last one, right here, well, infinity is a value that does not make the fundamental theorem of calculus happy. Fundamental theorem of calculus does not work with infinity sitting there on the endpoint. So we say, all right, fine, we won't use infinity. We'll just stop at some point c. Yeah, right here. Right there's c. And we'll get that integral done. The result will have c's floating around. And then we're just going to ask, well, what happens as c goes to infinity? This is how you disassemble an improper integral and cheat your way through the fundamental theorem of calculus. There's one last other subtlety here, and that's in the value of the limit point. This says limit as a approaches -1, right? Well, here's -1. The pen is now pointing to -1. When we're in the interval between -2 and a point which is really close to -1, we are approaching -1 from the left, and so as you remember, that means we should probably put a little minus on that 1. In this middle integral, we're on the interval from not quite -1 up to 5, and so we would be near -1 but over to the right, and so in our limit we would be approaching -1 from the right. And then over here there's only one way to approach infinity, so we don't have to touch it up at all. Now, how do you evaluate one of these? Well, I'll do one and then I'll let you do the others. This one right here, based on the work we already did, will be -1 over 1 plus x evaluated from -2 to a, which will be -1 over 1 plus a minus -1 over 1 plus -2. which is negative 1 over 1 plus a plus, 2 minus signs makes a plus, 1 over 1 plus negative 2 is negative 1. A little more. So this antiderivative with endpoints of negative 2 into a, we go through the antiderivative, plug in those two endpoints. We're using the fundamental theorem because there's nothing wrong with this integral at that point. Get the antiderivative, plug in the endpoints, shake it out. And then we remember, oh wait, I got to see what happens as a approaches negative 1 from the left. Oops, let me scoot this up just a bit. Look what happened. After all this work, we started up here. We broke apart our big interval of integration because there were points for the function. We isolated each point as a single endpoint of a subinterval of integration. We broke apart the original integral into 3 individual pieces so that we could avoid trouble spots with the fundamental theorem. We got rid of the trouble points with use of parameters just so we could trick the fundamental theorem of calculus into working. And then after the fundamental theorem of calculus did its job, we went back and said, haha, fundamental theorem, I'm just going to take a limit as I approach that point anyway. And what we've done is we've ended up needing to evaluate a limit which doesn't exist. And that means that after all this work, that integral doesn't exist. There is no value for it. It took us a lot of work to find that out. But what are you going to do?